All right. Oh, gosh. How's it going? All right. Very nice. Hey. All right, guys, let's go ahead and get started. So just a couple of reminders about the course logistics that we have. Today is lecture 14, Tuesday the 10th. And we have one more lecture on Thursday, then the midterm on 17th. All right, so it's an in-class midterm. You can bring your computers. You can use all your notes from the course. You could bring your book for the course. It's going to be 1 or 2 homework style problems that you have to solve in 1 hour and 15 minutes. All right, so my suggestion is to be as verbose as possible. Try to just write out your thoughts. It's just like the homework. You got to discuss your observations and do some kind of derivation on some electromagnetics problem. All right. Very good. So if you've been able to do your homework lately, then it won't be an issue. It should be easy. Okay. Then we have lecture 16 and another reminder about lecture 17. Only on this day, we're going to be across the hall in Torg 1030 from 8 to 9:15. All right. So we got to make sure we don't forget that. And if one more change to the syllabus, we had homework number 4 due on the 19th, which would have meant that it would have been assigned on the 15th. I'll probably still give it to you on the Thursday, but it will now be due on the following Tuesday so that you don't have to worry about it till after your midterm. Then from the midterm on, you'll have a whole week to do it. All right? All right, very good. Other than that, is there any questions from last lecture? Okay. All right. Let's get into it then. What are we talking about? We're talking about polarization of electromagnetic waves. We've been studying electromagnetics starting from Maxwell's equations. We recast Maxwell's equations into the wave equation. We solved the wave equation by separation of variables in various coordinate systems, rectangular, cylindrical, spherical, to find out what kind of mathematical descriptions do we have to describe electromagnetic waves, right? Electromagnetic fields. For example, when you turn on the light switch in this room, it fills the entire room with electromagnetic waves, right? There's an electromagnetic field in this room right now, and at any given x, y, and z point that I could describe, I can assign a vector to that point. That vector has magnitude and direction, and it oscillates in time. For us in this course, we're assuming time harmonic excitation, meaning that due to linearity of Maxwell's equations, the field vectors also vary sinusoidally, right? If the source varies sinusoidally, so do the field vectors. Therefore, we can remove time and work in the time harmonic domain, as we saw, and we can solve for sort of a snapshot, a temporal snapshot of what the electric field would look like. All right? But most amazingly, that light, it sends electromagnetic waves into this room. They bounce off of everything and they reach a steady state configuration. So at every point in this room, there's some vector. Now, we know by solving the wave equation, the only solutions that we have available to us in the palm of our hand to describe this electromagnetic field is sine, cosine for rectangular, exponential for rectangular. And then in cylindrical, what do we have? Bessel functions and Hankel functions. And azimuthal was also exponential. In spherical coordinates, we had the spherical Bessel, spherical Hankel, and so forth, right? And Legendre polynomials, Legendre functions. What I'm trying to get at is, no matter what the configuration of the electromagnetic field in this room, it can be described with those simple functions, weighted combinations of those simple functions, right? So you should feel powerful. You should feel like I've taken Maxwell's equations, I've solved this couple pair of differential equations, and I've come up with some functions I can write down on a piece of paper, and I can describe any electromagnetic field in this room, for example, right? But you know, that gave us eigenfunctions, right? What we can use to write down the electromagnetic field, but still there's some unknowns, the wave numbers and the coefficients, which we have to apply boundary conditions. And that's when this problem becomes intractable, right? So then you reach to your electromagnetic simulation software to model up the desks in this room and so forth. Okay, so then we looked at unbounded media. So we knew what functions we had to describe electromagnetic waves. What were the properties, right? What attributes did they have that we could use to describe different electromagnetic waves? We looked at wave impedance, we looked at phase velocity, group velocity, and so forth. And we got here, right? Now we're talking about polarization of electromagnetic waves. So electromagnetic waves are transverse waves, meaning that the electric field oscillates in a plane transverse to the direction of propagation. Remember, we defined this particular type of mode as transverse electromagnetic, and they travel in some direction, right? So in this case, there are three general, or not general, but three cases of polarization that we're going to study in this course. The first is linear polarization. We saw this last lecture, where the electric field is oscillating. Okay, so let's read the definition so we can understand these pictures. The polarization of a uniform plane wave. What does uniform plane wave mean? Do you remember?
It's just infinite across.
So the word plane, right? So that means there's something special about a plane, orthogonal to the direction of propagation. That plane has two properties, right? A wave has amplitude and phase. A uniform plane wave is a particular type of plane wave that has both uniform amplitude and uniform phase in the plane perpendicular to the direction of propagation, right? So if I have a plane wave traveling in this direction in the room, in that direction, I can cut that plane wave with an infinite plane. And that infinite plane, if it has uniform phase and uniform amplitude, then that is a uniform plane wave. Being uniform, that means that it's not a function, it's constant. It's not a function of the transverse coordinates. So that plane wave is the most easy to describe. E to the minus j beta z, right? With nothing, no coordinate dependence on x and y. Anyhow, the polarization of a uniform plane wave describes the locus traced by the tip of the E field vector in the plane orthogonal to the direction of propagation at a given point in space as a function of time. So there's a lot of words. Let's unpack it. First, we have to look in the plane orthogonal to the direction of propagation. This plane wave is traveling in the z direction. So the plane orthogonal to the propagation direction is xy. That xy plane is where we're going to do our observations, right? So it's at a point in space, at a given point in space, meaning if I change my z coordinate, then I might get a different definition of polarization. I'm looking at this particular direction, this z, right? And this x and y. So I'm looking this way, right? But if I look over here, then maybe I get a different different definition of polarization, all right? At a particular point in space is a function of time. So each point in space gets assigned to polarization. And we have to look at the electric field vector, the locus traced by the tip of it as a function of time. So here's the tip of the electric field vector in a plane at a point in space, at this x naught, y naught, z naught, in a plane orthogonal to the direction of propagation. I want to look at the tip of the electric field vector and the curve that it traces as a function of time, right? In this case, for a plane wave or for a linearly polarized wave, that locus is a line, right? That's a linear polarization. In this case, we have circular polarization. If you follow the tip of the electric field vector, then we end up tracing out a circle. So that's circular polarization. And finally, the general case is elliptical polarization. All right? So we'll study all three of these. Okay, jumping ahead real quick. How can we get circular, how can we get the electric field vector to rotate in a circle, right? So here, look, we have two components. First off, it requires we have two components. We're gonna study this in this lecture. Has to have an x and a y component. That x and y component have to be equal in amplitude. And if you look at the phase delay between these two, it's 90 degrees, right? 90 degrees means that one is maximum when one is minimum. Think of sine and cosine. Sine is a maximum at z equal to 0. Sorry, cosine is a maximum at z equal to 0. And sine is a 0, right? At z equal to 0. So those are maximum and minima at different times, or maximum, minimum at the same time, right? So if you have that special case, equal amplitudes, 90-degree phase difference, then when you superimpose Ex and Ey into the actual electric field vector, then that vector appears to be a vector which rotates in a circle, right? Okay, we'll study that. So that's how you get circular polarization, all right? One thing we have to remember, when we look at these plots, they're somewhat misleading. It tells you about the amplitude of the electric field vector, right? Along this line, and it's in the plane, and it's showing you a sinusoid, right? But really what it's representing is an entire plane of electric field vectors. So this sinusoid graph, you have to expand in your mind into a whole plane, an infinite plane like this, all right? So this is a maximum point. This sinusoid has a maximum. That means that the plane that's orthogonal to this axis at this point has this amplitude for all the vectors in the plane orthogonal infinitely, right? There's a plane. Then it becomes a minimum, it goes to 0, then a negative maximum, right? But these are vectors that are everywhere in that plane orthogonal. And we looked at linear polarization, so I'll go through it kind of quickly. Okay, remember also that this is E and H here, right? See, if you have two components, which was a requirement for CP that I mentioned before, and they're both the same amplitude, that's another checked box, but they're in phase. So if you add that electric field, the X and the Y, you'll just get a diagonal, right? And that diagonal will still trace a line in space. So they have to be 90 degrees out of phase to get CP. We'll see that. So this just shows that they oscillate as a function of time sinusoidally, right? But that shows E and H, so it's kind of misleading. There are not two components of the electric field in this case. E vertically oscillates, and then there's H there too. All right, so we have the electric field. We have to trace this electric field and find its locus as a function of time. So we need to work with the instantaneous electric fields, right? Script E, we have an X and a Y component in general, right? Why? Because we're looking at plane waves, right? Plane waves only have components orthogonal to the direction of propagation. TEM, transverse electric and transverse magnetic, transverse electric magnetic, right? So there can be no component in the direction of propagation. So the general electric field has no Z component because we're assuming that the wave travels in the Z direction. We can write the electric field as a function of time, the instantaneous electric field, as the real part of our complex electric field, time harmonic, multiplied by e to the j omega t. And then we take the real part, right? We know that. X and Y component, they have different amplitudes in general, and they have the same frequency, of course, and the same propagation constant because it's a plane wave, but what's not explicit, okay, yeah, so it is here. So then this equals 2. We're gonna separate, remember, in time harmonic domain, what is the price we paid to solve the wave equation independent of time? Derive Maxwell's equations that were independent of the temporal coordinates, right? What is the price we paid? Do you remember? What's that? Complex arithmetic. So nothing is real valued anymore. These are real valued. Now we have complex valued functions, right? So we have to work in a complex domain, but we don't have to worry about time, which is good. So that means this is a complex coefficient. It has amplitude and phase. It's a complex number. So its amplitude is denoted EX naught, and it has a phase, E, so this in polar form has e to the j phi x. We combine it with this exponential, we take the real part, we get cosine, so we have some phase associated with the x component. And that phase is encapsulated in this complex amplitude. Same thing with the y component, EY naught and phi y. This is the general form of the electric field for all cases of polarization we're going to study. All right, so we need to check in a particular plane, orthogonal to the direction of propagation. We're going to choose equal to 0. It's the most convenient. At z equal to 0, these two terms, they go to 0, right? The two phase terms in the argument, beta z. So less worry, right? Less to worry about. We have z equal to 0, we can remove those two components. Okay. Furthermore, we're going to assume for now that EY naught is equal to 0, so we have only one component, the EX naught component. So this is our electric field for this particular assumption. All right, this is a straight line, right? There's only one component, EX, so there's no way that electric field can leave that x-axis, and it will always be directed along the x-axis at all times. We call that linear polarized in the x direction. All right? Polarization is very important to understand. If you design any communication systems, if you design anything with antennas or point-to-point links, or even scattering problems, you could have polarimetric radar, where you try to measure rainfall or something, and you send an electromagnetic wave to it. And because of the raindrop being spheroidal, right, it's not perfect sphere, then you want to measure the response due to both polarizations. So you need to know the polarization of an electromagnetic wave. You need to design your antenna to launch that electromagnetic wave's polarization, that polarization. And you need to know the properties of your scatter. Maybe they rotate polarization, or maybe they take one polarization and send back two, right? So there's information in the polarization. You can also pack information in communication systems on different polarizations since they are orthogonal. All right? Okay. All right. So then there's also the case of the y-axis when EX is 0. We looked at that last time, linear polarized in the y direction. You can have a combination of both. If both are non-zero, then you have EX naught equal to EY naught. The phase delays are 0. They have to be in phase or 180 degrees out of phase. We'll still give you a line. And you can obviously use your polar form of equations to find the magnitude of phase of the combination of the actual electric field. X squared plus Y squared square root and inverse tangent EY over X. All right, we saw that last time. Also linear polarized. All right, so let's get into CP. All right, any questions on LP? All right, very good. All right, CP. Okay, so CP, there are two cases. Remember, first off, what I told you last time. If this is the hand of a clock, right, minute hand, and it's rotating this way, for you guys, it's what? Counterclockwise. But for me, I see clockwise, right? If I turn around and I keep going, so right here, from here toward my right shoulder, right? It's counterclockwise. Now I go like this, and now I'm seeing your perspective toward my right shoulder is clockwise now, right? So there's an ambiguity. We have to define a convention to break that ambiguity. If we're going to talk about a rotative sense, it could either be clockwise or counterclockwise, but we have to say from whose perspective. So when we define circular polarization, we're going to define it as behind the wave. The wave always travels away from us. So your perspective would be incorrect, or it's not incorrect, it's not convention, right? As long as you're upfront about the convention in a paper you might publish, then that'll be okay. But the standard convention, at least for the book reason for this course, is we're behind the wave. So the wave's traveling that way. So this way would be clockwise, yeah? Okay. Here's our electric field vector again in general, right? It has both an X and Y component, an arbitrary phase delay and arbitrary amplitudes. In the plane Z equal to 0, if we assume we have equal amplitudes, that's one requirement for circular polarization, and we choose phi X equal to 0 and phi Y equal to minus pi over 2, 90 degrees out of phase, then we get EX is equal to ER cosine omega t because phi X is 0. We're looking at Z equal to 0 plane, and we have an EX component with EX naught amplitude, but EX naught and EY naught are equal. We call it ER for right hand, and we get cosine omega t, right? For the other component, EY, we have EY naught, cosine of omega t, this phi Y is minus pi over 2, and beta Z 0. This cosine of omega t minus pi over 2, if you imagine the cosine function and you translate it to the left along the negative axis by half of or pi over 2, you get sine, right? Okay, good. All right. So here's our X and Y components of the electric field vector. We'll see in the next slide when you superimpose these that you get this thing to rotate, right? Here is the electric field vector. So this is how we're going to plot when we want to determine the sense of polarization of any electromagnetic wave. We're going to plot it like this. Why do we have, where's the Z-axis pointed? Into the board. Why? Very good, but why have we chosen it to go into the board? Very good. We need to be behind the wave, right? So always, when you draw these locusts of the electric field vector as a function of time, you want the Z-axis going into the board. You might get a problem where it says it's traveling in the Y direction, then the Y-axis goes into the board, right? So be cognizant. Okay, now, if the Z-axis goes into the board, we have a right-handed coordinate system, then the X-axis must be vertical. X cross Y gives you Z. Normally, you put the X-axis on the horizontal line, right? But the Z-axis is soon to come out of the board. So remember, X-axis vertical, Y-axis that way, and then Z into the board. Now all I have to do is take omega t as a whole number. Omega t equal to 0, omega t equal to pi over 4, omega t equal to pi over 2. And I just plug that into these two functions, and I get the X and Y components, and I can plot them at all these different times. And if I follow what happens as time increases, then the vector starts to rotate clockwise. All right? Yes?
So if we replace pi by with positive pi by 2, will it become left circular polarized?
It is. Yeah, we'll see that next.
Okay. So if we actually implement an antenna, in what cases do we require a right circular polarized antenna? What's the difference in implementation?
Very good. So there's a lot of, so it's up to you, right? It's a design degree of freedom. Right CP and LHCP are orthogonal. So an LHCP antenna cannot communicate with an RHCP antenna, right? They're orthogonal polarizations. One common use of CP is, say you have some satellite or a communication system that is transmitting or broadcasting electromagnetic waves like cellular systems, right? Normally those are CP. And why? Because your handset, it's not guaranteed. Your handset sometimes is linear polarized, right? And it's not guaranteed how you're going to be holding it. So let's say that the base station was vertically polarized. If you're talking on your phone like this, you're going to get no signal. So if it's CP though, and it spins, no matter what orientation I have my phone in, I'll get, at least 3 dB down, right?
Like, how do we decide if we have to make it a right circular polarized or left circular polarized?
That's your choice, right? So typically a system designer will come up with these properties, right? If you have a big project and they'll decide, okay, this polarization maybe because maybe it does better in the rain or some kind of property that they're trying to exploit based on which polarization they pick. But the system designer will kind of do the study and the analysis of the channel and figure out which polarization is best. And then the antenna designer will make an antenna with that polarization. But LHCP and RHCP, very similar, right? They're just orthogonal. Okay, great. So remember, this thing is showing a locus, which is like a spiral in space, but you need to expand. This just tells you the magnitude of the electric field vectors in the plane orthogonal, infinite plane orthogonal. So at this point, we have the magnitude of the vertical component is maximum. The magnitude of the horizontal component is 0. So in this plane, we have all vertical components, right? So this spiral just tells you what amplitude all the vectors are in the plane orthogonal to that, right? So expand it in your mind to plane waves.
Does that mean the magnetic field is also polarized in the circle?
Yes, definitely. Yeah, I mean, as a matter of fact, this is the electric and magnetic field. So you see this more bold vector rotating. That's the electric field. And orthogonal to the electric field is always the magnetic field. And for a uniform plane wave, it's along for the ride, right?
So plane wave is always TEM?
Plane waves are TEM modes, yes. Yes, there are uniform plane waves where the phase and amplitude are uniform. There are plane waves, TEM modes, which at least the phase has to be uniform. If the phase is uniform, the wave front is defined by the phase on that geometric entity, right? There are cylindrical waves, spherical waves, but all of these mean that the phase is uniform along this particular geometry. Good question. You remember why we only have to solve for the electric field, right? Once you have the electric field, everything's known, right? Why?
Because you can use various ladder.
Very good. Excellent. So that means the electric field gives us everything we need. All right, so so this is what I already told you, right? This is how you solve the problems. You start with the general form of E, you specialize it to Z equal to 0, you draw your XYZ coordinate system, and then you have EX at 0, Z equal to 0 in time, EY at Z equal to 0 in time. And this is how I solved my homework problems when I did this course. Omega T table, EX, EY. And you just pick a couple of numbers for omega T, and you plot them. So the first one is here, omega T equal to 0. Then omega T equal to pi over 2. Then pi, 3 pi over 2, and so forth. We know that it rotates clockwise. Okay, clockwise, you can either remember that clockwise is RHCP and anti-clockwise LHCP, or you can use your hands. So what you do with your hands is you point your thumb. We'll see it on the next slide. You point your thumb in the direction of propagation, into the board. You rotate your fingers from the phase leading to phase lagging component, or in other words, in the direction of the rotating vector. If you plot it like this and you know which direction it's going. So thumb in the direction of propagation, rotate my fingers in the direction of the evolution of the electric field vector as a function of time. My right hand is following the correct direction, right? If I use my left hand, thumb in the direction of propagation, then it should have been counterclockwise, yeah? So LHCP uses your left hand, RHCP uses your right hand. Question?
How does relativity, like if we have multiple observers and we have relativity, like how does the observation of what the phase of the polarization is?
Okay, so relativity, that's beyond the scope of the course. Let me just give you a quick answer. If you had, depending on the motion of the observer, there's a different form of, so Maxwell's equations holds in all of these cases, right? They're relativistically invariant. I haven't ever sat and thought about that, so I don't want to give you an answer that where, you know, you have motion and a, you know, relative motion, and I'd have to think about it. But come by my office, we can talk about that. Sounds fun. Okay, good. All right, so RHCP, we saw this already. We have two components. We could find the amplitude of the component as the square root of EX squared plus EY squared. This is ER squared cosine squared. We derived that on the last slide, plus ER squared sine squared. ER is the same, it comes out. Cosine squared plus sine squared is 1, we get ER. We could find the direction as inverse tangent of EY over EX. Well, sine over cosine is tangent, so inverse tangent of this becomes, these cancel, and you get inverse tangent of tangent, you just get omega t. So the direction is changing with a function as a function of time, right? And we expect that. Omega t is the angular direction. So, okay, very good. So, and then here's the right-hand thing. Because the field is rotating clockwise and viewed from behind the wave, the field is RHCP. You can put your thumb in the direction of propagation. This says direction of propagation. This says rotation of fingers. RHCP allows you to do that with your hand, all right? All right, questions? Good. So yeah, we got to get through these, like, we need to be able to speak the language to each other about plane waves and electromagnetic fields. We got to learn all these properties. So in order to, you know, communicate your ideas in electromagnetic theory, you have to know the language, right? So we'll get through all these properties and things. We'll start doing some really fun things with scattering and things like that. All right, here is a way to solve it. So, okay, before we solved it all in the instantaneous domain, the time domain, right? We needed the electric field in the time domain. We needed to plot its locus as a function of time. What if we want to solve the problem completely in the time harmonic domain when we have the complex fields? Because that's where we're doing all of our work, right? We transform into this domain, in the phasor domain. We do all of our, we solve Maxwell's equations in that domain. Even the simulation software does that, as long as if you're using finite or frequency domain solvers, right? So to go back to the time domain, e to the j omega t, multiply by that and take the real part is usually an implicit step. You don't publish that normally. You might, right? There might be cases where time is important, where you're not considering sinusoidal sources. But we need to be able to solve this in the complex domain. We should be able to do that. So here we have EX naught equal to EY naught equal to ER for CP, right-handed CP. Delta phi is the phase difference between two components, has to be pi over 2, right? All right, or odd multiples of, we'll see. So we can write the complex fields as, remember, this is not a script E, this is E, there's no time here, this is just E of Z. It's X hat E, right? Because we've assigned phi equal to 0. This is the complex amplitude. There's the E to the minus JKZ propagation factor. And we have E, right? E to the minus J pi over 2. So we've added the phase delay back into this. So we've written the Y component's amplitude in polar form, right? Okay. We can factor out the ER, and we have X hat, and we call this minus J Y hat. Why? Because E to the minus J pi over 2 is J, right? You guys know that, yeah? Or minus J. If you use Euler's identity, cosine of this argument minus J sine of that argument, and then you plot that on the real and imaginary axis, you'll see that E to the minus J pi over 2 is minus J. All right? So here is our complex form of the CP wave, the right-handed CP. Minus J means whenever you see a J, we know we should associate that with a phase delay of 90 degrees, right? From Euler's identity, exactly. So minus J means that Y hat is lagging by 90 degrees. If it were plus J, then Y hat would be leading by 90 degrees. All right? Now we use this right-handed hand trick thing. So we point our thumb in the direction of propagation. We rotate our fingers from phase leading to phase lagging. So let's try it with the right hand. I put my thumb in the direction of propagation. Phase leading is what? This is minus J behind X. Y is minus J behind X. 90 degrees behind. So X hat component is leading, right? So I rotate my fingers. X is vertical in this coordinate system from phase leading to phase lagging, from X to Y, right-handed CP. If I did it with my left hand, then phase leading to phase lagging is X, then it would go to minus Y, but then this would be a plus, right? So you can see you can use your hands to solve for the polarization state. So here are the rules. Always observe the wave in the z equal to 0 plane. Always observe from behind the wave. Point your thumb of the right hand in the direction of travel. Rotate your fingers from the phase leading to the phase lagging component. The hardest part of that is which component is leading, which one is lagging. And then if it's your right hand, if this is successful, then it's RHCP. If not, repeat with the left hand. If this is successful, then it's an LHCP wave.
Practical to modulate the X and Y components so we can just encode information into the polarization.
Yeah, definitely. Yeah, communication systems, you can design a communication system that encodes information on different polarizations in order to pack more information into the channel.
So we can just do like orthogonal kind of modulation schemes where the functions are orthogonal. So we have some weird trace in the XY plane.
Yeah. You can do, the problem with that is you have to have very controlled orientations of your antennas because you're putting information on the different polarization components. So you want to make sure that when you send X, it gets received X. So both you should have probably a fixed transmitter receiver, right? But yes, you can do that. And hopefully your channel is not anisotropic or doesn't do anything to the polarization.
So we don't have to worry about bandwidth. If we have a scheme like we're playing tricks with the phase to pack more information.
Yeah, very good. Okay, good. All right, here's an example. Okay, let's go through the example. An RHC polarized plane wave with the electric field magnitude of 3 millivolts per meter is traveling in the plus y direction in a dielectric medium with epsilon equal to 4 epsilon naught, mu equal to mu naught, and sigma equal to 0. Sigma equal to 0 means lossless medium. Very good. If the frequency is 100 megahertz, obtain expressions for E and H as a function of Y and time, right? So pick a field component to be the reference. So we want to pick one to be the reference. We were picking X before, right? You could pick either. In this case, let's choose the vertical axis as before. So Y direction is now into the board because it's traveling along the Y direction. We need to pick either X or Z to be our reference, right? So we pick Z. Now thumb in the direction of propagation, or sorry, X crossed with Y has to give us Z, right? For a right-handed orthogonal coordinate system. X crossed with Y gives us Z. So it's good, right? So we put V or Z vertical. The reference is Z component. Since we are told the handedness is right-hand circular polarized, we know that the amplitudes are equal and the phase difference is pi over 2. So let's write down immediately what the electric field is. The electric field is a function of Y. Okay, so don't worry about this tilde. That should not be there. There should be a vector. The electric field is a function of Y is equal to X hat E right, E to the minus J pi over 2 plus Z hat ER. So we have X and Z components here. The Z component is our phase of reference, so we're going to choose it to have 0 phase. And our X hat is has a 90-degree phase delay, right? We set it here, delta phi. It's lagging by 90 degrees because it's RHCP, and we have E right. And then E to the minus JKY. So this in polar form is converting this component into a minus J. X is lagging by 90 degrees. And we can then just turn the crank. Once you set up the problem, it's all arithmetic from there. All right? So you can find the electric field. Once you have the electric field, you can find the magnetic field. How do we find this magnetic field fast for a plane wave? You guys remember? We don't need to use Faraday's law for plane waves. We use our right-hand rule. E cross H is always direction of propagation. So E cross H is K. We know E and K already, so we can find H, the direction. And then we divide by the wave impedance, right? Not A to C because it's a lossless medium, it's eta. You remember that, right? Okay, good. All right. Okay, let's do LHCP. So now, I'm not going to go through this in super gory detail here, but the only difference between this case and the right-hand circular polarization is now we require a minus pi over 2 phase delay. All right. So when these two are 90 degrees out of phase, but it's an odd phase, right? Minus pi over 2, or sorry, a negative phase delay, then you get LHCP, right? So one's plus and the other one is minus. And you see if you do this inverse tangent that you get minus omega t, which means with time, angle is changing negatively, right? And you can use your left-hand rule. This is all exactly an analogous case, all right? You can look through here on the slides when you get home. Okay, so then there's some rules for linear polarization, circular polarization. So for CP, the field component, okay, so first let's do LP. LP, we need at least, you can either have a single component or two orthogonal linearly polarized components that are in time phase or 180 degrees out of phase. So not 90 degrees, either 0 degrees phase or 180 degrees phase. Either one or two components. But if you have two components, they have to be in phase or 180 degrees out of phase. For CP, we have to have two components, orthogonal components, and the two components must be the same magnitude, and they must be out of phase by odd multiples of 90 degrees. Why odd multiples? Because an even multiple of 90 degrees is 180 degrees or 0, which is linear polarized, right? So it has to be odd multiples of 90 degrees. And you can find the sense of rotation using the phase leading to lagging trick with the hands. All right, so elliptical polarization. Let me just see how deep we get into Okay, cool. Let's see if we can get an propagation and anisotropic media. So we're almost to that. Okay, good. I think we'll get there. So elliptical polarization is the general case, right? Elliptical polarization has different amplitudes. Remember, CP, we had to have the same amplitudes and a particular phase difference. Elliptical polarization is general amplitudes, any two amplitudes and any phase delay between the two. So most of the time you'll be elliptically polarized unless, okay, so if you have the conditions to meet elliptical polarization, right? You either have specific conditions to meet LP or you have only one component, you get LP, or you design it to have CP where you have a specific phase delay in your source between the two components. Or if you don't have those two cases, the rest is EP, right? Elliptical polarization. All right, so if the necessary and sufficient conditions that we described on the last slide are not met for either LP or CP, then it's elliptical polarization. Here's our electric field again, the general form. At z equal to 0, we get rid of the z's. And if we assume that EX naught is E right plus E left, we're gonna write it that way. So this is some constant, EX naught, right? We're just gonna call it EL plus ER, all right? And then Y is ER minus EL. We'll see why we do that. It allows us to define the axes of an ellipse. And phi X is pi over 2 and phi Y is 0. So we're gonna study this particular case where we do have 90-degree phase delay, but the amplitudes are different, right? So you can already imagine if the amplitudes are different, but they're still 90 degrees out of phase, then by the same figure as we had before, try to imagine this figure where they're still 90 degrees out of phase, but when this one, red one is 0, the blue one is super long. And when the blue one goes to 0, the red one is short, right? They don't have the same amplitude. So it's still gonna trace out, they're gonna add up together and trace out some kind of figure, but it's going to be elliptical now, yeah? So the first thing we notice is we can get EP if the amplitudes are not the same. So EX, we've defined EY naught as minus ER, or sorry, ER plus EL, right? And then we have, wait a minute. This should be EX naught, right? ER minus EL is, yeah, okay. So make the change in your notes. Whoops. This is EX naught. All right, EX naught, cosine of omega t plus pi over 2. We define the phase angle of phi of the x component to be pi over 2. Cosine of pi over 2 with a positive phase delay or phase shift added to the cosine, it becomes minus sign, ER plus EL. And then we have EX, ER minus EL cosine of omega t because it has no phase delay and we're looking at z equal to 0 plane. All right, E, we can find E squared now, which is EX squared plus EY squared. And if you do the math, you'll end up reducing it to this expression here. ER squared plus EL squared plus 2ER EL sine of omega t squared minus cosine of omega t squared. All right. Okay. Now what we're going to do is we're going to write sine and cosine in this form. EX we know is here. EX is ER minus EL cosine of omega t. Something's not right. This should be EY, that's what it is. So sorry, so when I made these notes, I did copy and paste a lot. I made all these over the summer, so that's EY, right? Obviously, this is EY. ER minus EL is EY. So this should be a EY too then. All right.
So if we have circular polarization, ER would be equal to EL, but then wouldn't
Oh, wait a minute.
it be 0?
1 second, let me just notify everybody that that is correct. The equation at the bottom is correct. Okay, but what, say it one more time?
If we're using elliptical as a general for a circular polarization, ER would be equal to EL.
Yes.
So then E min would be 0. So then wouldn't that be linear polarized?
Well, if it was ER, if it was right-handed CP, then EL is equal to 0 and ER is equal to ER. So then it would be ER here and ER there, right? ER is not equal to EL. Is right-hand circular polarization only has ER.
Oh,
Left-hand only has EL.
oh, so they're just kind of flip-flopping between the two. Okay.
Okay, so we notice from here that we can get cosine is equal to EY divided by ER minus EL. Sine is equal to minus EX over ER plus EL. And we can then rewrite this equation, or we can do sine squared plus cosine squared equal to 1 like that. Okay, which is an equation of an ellipse with the major axis of ER plus EL and a minor axis of ER minus EL. So that's the reason why we chose those constants, the way to represent those constants, EX naught and EY naught, as the summation of ER plus EL and the subtraction, the difference. Okay? Yes?
Is it like accurate to consider CP and LP to be special cases of elliptical?
It is very accurate. Yes, that is correct. The elliptical polarization is the most general, right? All these numbers are different. They can be anything, phi y, phi x, EX naught, and EY naught. If you specialize those to particular cases, then you get CP and LP, right? So this is the general case.
Okay, and then also the second bullet point says like assuming that the phase differences for X and Y are like off by 90 degrees, but that's not necessarily true, right?
If
Like
it doesn't have to be.
It doesn't have to be.
We're studying this particular case first, where we've specified these to be 90 degrees and different amplitudes, just to kind of highlight the difference between CP and EP, that the amplitudes matter, right?
Okay, yeah, that makes sense.
Very good. It becomes very hard to solve if you let those be arbitrary. The elliptical polarization can get kind of hairy.
Because then you would have cosine and sine.
Yeah, these expressions become a little harder to combine, right?
What controls the frequency of the phase rotation? Like, how fast is it?
Omega, right? So remember we solved for that here. This is the angle, this psi angle is the angle that's made between the horizontal axis and this vector. That angle, as a function of time, tells you how fast it rotates, and it's the frequency, right? The angle is equal to minus omega t. So the higher the frequency, the faster it rotates.
Phase are always going to be linked. You can't have a phase faster than frequency.
That's right. Because remember, these things are oscillating in time, right? This is oscillating sinusoidally, right? Or cosinusoidally. Same with this component. Now, if this is sine of omega t or sine of t, then it's going to oscillate slowly. But if it's sine of, 10 to the 6 t, then it's going to be oscillating very fast. And when you add those two together, it's going to start spinning way faster. Yes. Okay. So, so let's look at this big expression now. Let's look at this in terms of, so here's our time-dependent electric field. We can write that as, this is our specialized case to the CP that we studied on the last slide, right? This has no phase delay. This is 90-degree phase ahead. Then we have ER plus EL and ER minus EL. We can write that, multiply by e to j omega t and take the real part. Then we can start to write this in terms of the complex field, right? The e to the plus j over 2, e to the plus j pi over 2 becomes a plus j. And we can write this in this complex form here. And if we rearrange some terms, So we solve for ER and solve for EL. What we notice is something very interesting. The elliptical polarized wave can be considered as, or can be expressed in terms of the superposition of an RHCP wave and an LHCP wave. These things will become, these are the kind of tricks that you pull out of your bag when you want to design something or when you want to analyze something. So we study these in this course when we're studying polarization, right? But when we become creative, which makes us even better engineers, we have knowledge, we are able to assemble new ideas from that pool of knowledge we have. Creativity leads to new technologies and things. And these are the types of expressions that allow you to be creative, right? Oh, what if I make an RHCP and an LHCP wave? I can add them, I can do something interesting with polarization. It's a medium, right? So try to think that way as you're learning these things. Keep these as facts that you can draw from creatively, all right? So this is one case where we'll see something in anisotropy that we're going to study next, where we have different kinds of polarizations that come out of anisotropic media. All right, so elliptically polarized wave can be expressed as a sum of an RHCP and LHCP wave, right? If ER is greater than EL, then the elliptically polarized wave is right-hand elliptically polarized with an axial ratio expressed like this, and it's negative. If on the other hand, no pun intended, I guess I wrote, E right is less than EL, the wave is left-hand EP, and the axial ratio is positive. Okay, so since the linear polarization is a special case of elliptical, we can also express an LP polarized wave as the sum of an RHCP wave and an LHCP wave. And this becomes useful in media with optical activity, where you have a different index of refraction along one axis than you do along the orthogonal axis. One wave travels at a different velocity. What happens then is an LP will be broken into two CP waves, right? We'll see that. I think I have that in the notes somewhere. So different ways to express. Okay, so there's some mathematics for a rotated ellipse. This is when the phase delay is not equal to pi/2, like you were saying, Amy. It becomes a little more difficult, but here are the mathematics for that. I'm not going to dig into it, all right? But if you want to refer to this, it's here in the notes. And these are general expressions to come up with the ellipse parameters, major and minor axes and the rotation angle of the ellipse axes with respect to the coordinate system. All right? Very good. All right. Any questions on polarization? Okay, good. So I'll tell you my experience with polarization and my research. When you design an antenna for a particular polarization, then it's generally a known polarization, and you need to be able to write down the expression of the plane waves or the cylindrical waves, whatever wave it is. You need to be able to write down the expression in terms of the intended polarization, right? So that's one thing you need to learn to do. And then say you design a metasurface, for example. I design metasurface where I come in with a particular polarization, and I can convert that into circular polarization upon transmission to the metasurface. If you do that in optics, there are things called wave plates, and they have a certain thickness to them, right? They have to be a quarter wave thick, right? And you can convert LP to CP if you have the right wave plate. But in metasurfaces, you could do that at the interface, the boundary, right? And you can design a metasurface to impose by that last expression, right? Remember, LP can be considered as RHCP and LHCP. You can do something like this. You need an anisotropic metasurface in order to do that. So polarization is important. If you design antennas for spacecraft, you need to be able to, you're going to solve problems in scattering where we're going to ask you to have a CP illuminating plane wave, and it scatters off of things, and you're going to investigate the properties of what happens to the polarization after it reflects, right? Things will happen. But normally when you design antenna, you know the polarization you're trying to get to, and it's kind of clear which geometry to approach, right? You need current to oscillate in the direction of the polarization that you want. So you need some kind of vertical strip of conductive material, for example, if I want vertical polarization. And if I don't want to excite any of the other polarization, then I want this to be thin. If I want both polarizations, maybe dual LP, then I can make a horizontal or diagonally directed metallic strip. And if you come in with vertical polarization, then if you project this, if you describe this diagonal metallic strip into its X and Y components, If I come in vertically, it responds. If I come in horizontally, it responds, right? Yeah.
How does the EX and EY change, we change the coordinate basis to cylindrical sphere?
So in that case, we won't be talking about plane waves, right? There'll be cylindrical waves. They have their own properties. Remember, we studied that with the Hankel functions. And to investigate the polarization. So in this course, we always have things that, I guess we can get all polarizations by combining. Remember, we have to solve the wave equation for z-directed components only. When we do scattering problems, we'll most likely have a z-directed electric field or a z-directed magnetic field, and we'll assume that the polarization doesn't change. These will be isotropic scatterers. But yeah, there are different components, right? In that case, you'll be talking about rho polarization, phi polarization, z polarization for cylindrical, and you can have E theta and E phi polarization and ER component, not in the far field, but ER. So there are different components to talk about in those coordinate systems. Generally, we'll probably, most likely what I do is assume that it's locally a plane wave. Even though it's a cylindrical wave or a spherical wave, remember by stationary phase approximation that we learned, we only get one, locally it looks like a single plane wave. Then you can talk about plane wave polarization, right? But in the theta phi R coordinate system. Okay, good. All right. So we learned wave propagation in infinite unbounded media. That's what we've been studying so far, right? We haven't introduced discontinuities in the media at all yet. We'll do that in next chapter. But in infinite unbounded media, we have all these different properties of the waves that we discussed. But so far, we've been talking about isotropic, linear, homogeneous media, right? The rest of this lecture, I've put in a few extra topics that are not in the book, which are due to, but there's readings, so you guys have material you can draw from. I've loaded them into the reading material folder on Canvas, where you can learn about what happens if the medium is not isotropic. What happens if it's not homogeneous? We'll cover that in the next class. So we're going to do 5106 next semester, cover inhomogeneous wave propagation in inhomogeneous media. And for that, we're going to have to solve, we're going to have to trace rays. We're going to use geometrical optics and geometrical theory of diffraction in order to handle inhomogeneous, because in inhomogeneous media, the wave vector is constantly changing direction, right? The K vector. So it's not a simple problem to solve in terms of these modes that we've derived using the wave equation, right? We have to approach it in a different way, differential geometry. But anisotropic media, the way K vector doesn't change, at least for particular directions, which is good for us. So, but interesting things happen to the electric field components. So let's study that first. So materials, and if you do metamaterials or if you do metasurfaces, then this is your playground here, right? When you study electromagnetic theory, you normally assume linear, isotropic, homogeneous media, all those goodies that make everything simple. But now you want to challenge yourself. What can I do with media? What can I do when a wave travels through a medium or enters into a block of material that I've engineered to give me new properties, or travels through an interface, right? So these are your things where you start to say, what if not linear? What if epsilon's near zero? What if I have negative epsilon? You know, what if it's not homogeneous? What if it's anisotropic? What can I get out of Maxwell's equations by exploiting these different parameters? So here we have linear, nonlinear, right? So materials whose constitutive parameters, epsilon, mu, sigma, right? That's how we brought in material media, are not a function of the applied field, are linear, right? Most materials are linear, but we treat them as linear within a certain range of field strengths. If you really apply a super strong field, some materials start ripping electrons off and so forth, and it will start to behave nonlinearly, right? The properties will change once you reach high field strengths, right? But everything we do here, linear, right? Homogeneous or inhomogeneous, a material whose constitutive parameters are not a function of position are said to be homogeneous. So that means epsilon, mu, and sigma, they are the same value. They're constant at all x, y, and z. It's a homogeneous media. Now, there was a lot of steps when we derived the wave equation where I kept saying to you guys, what is the assumption we made when we did this step? And it was always pulling epsilon, mu, or sigma out of a divergence or a curl, remember? And that was because it was constant, we could pull it out of the spatial derivatives, the divergence of the curl. But in the cases where you have divergence of epsilon E equal to rho, for example, we can't just pull sig or epsilon out, right? We have the divergence of a product, epsilon times E. So we have to use product rule and open that up. So Maxwell's equations take a different form for inhomogeneous media. We'll do all of that next semester. Okay, dispersive or non-dispersive, a material whose constitutive parameter is not a function of frequency. And most things are dispersive. Free space is not. All right? So at different frequencies, we get different permittivities, different permeabilities, different conductivities. And we expect that. Remember, in all of lecture 2, what did we study? Dispersion of permittivities, right? And we saw that there was strong frequency dependence. That strong frequency dependence allows us to design materials with negative permittivity, negative permeability, negative index of refraction, and get all this new phenomena, right? Dispersion is what we exploit a lot in guided wave phenomena. In this class, we're doing unguided or scattering problems. There is some structure illuminated with a wave, we scatter off of it, right? We calculate the electric field due to scattering. There's another whole regime of electromagnetics, which is guided wave problems, where we have a source and we excite a waveguide, and that waveguide channels electromagnetic energy in a certain direction. Like I said, right now I'm talking to you, I'm broadcasting. So my acoustic wave is going in all directions. But if I wanted to only talk to you, then I'm wasting energy in directions where I don't intend to send signal. So then I could guide an electromagnetic wave, in this case, an acoustic wave, by talking through a cardboard tube from a wrapping paper. And I guide my energy along that cardboard tube all the way to you, right? That's a waveguide. It guides an acoustic wave. How do I do that? I impose boundary conditions on my wave. The cardboard tube imposes boundary conditions. A rectangular waveguide is a metallic hollow pipe, which imposes boundary conditions impenetrable to the electromagnetic field, right? Guided waves have a lot of dispersion. We'll see that when we study rectangular waveguides, and well, I think in a different class, in metamaterials I taught last semester, there's a lot of dispersion relations you derive. So it's all about, when you study guided wave phenomena, it's all about the dispersion relation. We need to know the propagation constant of our wave. If we want to use this thing to transmit waves, we need to know how much phase delay we incur down the line. We need to know the wave impedance. All these things are functions of frequency now. Okay. Isotropic or anisotropic, we're going to study in this lecture. Materials whose constitutive parameters are not a function of the direction of the applied field, the electric field. I could have epsilon equal to 1 for the vertical, so I'm traveling this way. The vertical component sees permittivity equal to, let's say, 2. The horizontal component sees permittivity equal to 3. That's an anisotropic media. A lot of interesting things happen when you impose anisotropy into your media. All right? What's the first thing that we know of for the constitutive relation that epsilon appears? It's D equal to epsilon E. But epsilon is not a constant now. It's not a scalar either. It's a tensor. So it relates, this equation here, D equal to epsilon E, relates the electric field components to the electric flux density components, right? When this is a scalar, then dx goes to ex. dy goes to ey, dz goes to ez. Everything is lined up, right? But now we mix components. Anisotropy is super cool. I want to kind of hype it up to you guys, because if you do anything in metasurfaces, a lot of the stuff we do in our lab involves anisotropy, and what can we do with it, right? Mostly play with polarization. This is why. The polarization is what? The electric field direction, right? Now, if I have electric flux density, X component now depends not only on EX, but EY and EZ through these 3 scalar numbers, right? So there's a tensor that relates D and E. So assuming homogeneous, non-absorbing, magnetically isotropic media, what does all that mean? You guys should know. What is homogeneous?
Independent of position.
Very good. What is non-absorbing? Very nice. So what parameter is 0? For absorbing, lossless, sigma. Sigma 0. Magnetically isotropic, what does that mean? Mu is? Very good. Mu is constant. It's not a tensor, right? It's just a scalar. So then the only thing left is the permittivity. We described sigma and mu, and the permittivity is going to be now a function of, it's going to be anisotropic. The energy density of the stored electric field in the anisotropic medium now is different, right? We remember that the equation for the stored electric energy density is 1/2 epsilon dotted with D, right? What was epsilon? These are the time dependent ones, right? So we can substitute in what D is in terms of E. It is EIJ into EJ. That's nothing but this matrix multiplication. All right. Now, the power flow is the rate of change of energy with respect to time, right? Power is energy expenditure over time. So dUE, the dt, that's 1/2. So we differentiate this expression with respect to time. This is a function of time. So is this. We can write that in this form because we use product rule, right? These are all scalars, they come out. All right. The net power flow into a unit lossless volume. We did this in lecture 1 by using the conservation of energy theorem. Remember, what is E cross H? Say again? That's true. E cross H is the direction of K. In media which is right-handed media, which doesn't have any negative parameters, K is also parallel to the direction of power flow, S. So this is pointing vector, E cross H, right? The direction of power flow. The divergence, remember what we said about divergence. What does that divergence mean?
Whether that's a source or a sink.
Very good. It finds points of sources or sinks of this vector, of this pointing vector field, right? So we have a source or a sink. What does that mean when I add up the flux exiting some box that I surround a point with? If it's a source, what does that mean?
That would be positive.
And that means if I count up all the flux lines that are penetrating the surfaces of this box, very good. There's more going out than there are coming in. The net is positive, means something is in there that's creating flux. If it's 0, if I add up all the flux lines that are penetrating the surface of a box surrounding a point, and I get 0, then that means every flux line that came in must have exited. It means everything at that point is just a conduit for flux to go through, right? But if there's more coming out than there are going in, then there has to be a source of flux inside of that box. It's positive, it's a diverging field. If it's negative, it means a converging field. That means that if there's more going in than came out, then something must have absorbed some of that flux inside of that volume, right? That means it's a sink. So here we're talking about the divergence of the power. Power, E cross H, is a vector field, and it describes a flow of power. So the direction is the flow of the power flow. The magnitude is how much power, density. So I have a cubical volume. If I have, so this is some volume, right? If I calculate the divergence of the power flow, I'm adding up the power that's penetrating, the flux of power penetrating the surface that's surrounding that point, right? Or that volume. Let's say that I have more flux lines coming out than going in for that particular volume. What does that mean? That what's inside of that volume? So we're talking about power flux. If there's more power flux coming out than there is going in, it's a source of power in there, right? It has to be a source of power. If it's a source of power, then whatever is supplying that power, the energy density in there has to be decreasing with time. Because if power flowing out must mean that the energy density is decreasing, it's decaying. Think about the conservation of charge, conservation of current. If I have a volume and I calculate the flux of J, if there's more J coming out of that volume than going in, then that must mean that the charge density is decreasing because the J is the flux of current, which means charge is moving with respect to time, right? Charge is leaving the volume, charge must be decreasing inside, right? So here we have the divergence of E cross H. That if I add up all the power flux and some surface surrounding some point and let that point shrink to 0, so we can do this definition at every given point, then that has to equal to this number has to decay, right? We'll see that. Okay, so power flow into a lossless unit volume. This is our conservation theorem from lecture 1. Divergence of E cross H, the power that's flowing out of a medium, but there's a minus here, so it's a power flowing into the medium. So power flowing into a volume, a region, right? The net power flowing into the region must increase the power density in that region if there's power flowing into it. Net power flowing in. It doesn't flow in and go out. It goes in and stays. The energy density of the electric field and the magnetic field must be increasing, right? If I move this minus sign to the other side, it says the power flowing out. The net power flowing out must be decreasing the electric and magnetic energy density inside. Yeah? Let me make this last point real quick. So we know what D is in terms of E now, so we can use epsilon ij into DEJ, and then magnetic field stays like that. Yes?
So when we have matrices and these operators as tensors, and we have like the product rule, how do we decide whether we multiply to the left or right?
Okay, good question. So there, you mean this dot product, right? So typically, if you write it like this, then you have epsilon dotted with E, so you have a vector multiplied by a matrix to give you another vector. There are entities, mathematical constructs called dyadics. We're going to study all of those next semester. We've introduced them this semester. Dyadics, you can do a posterior and an anterior dot product with a dyadic. But hold that thought till next semester, right? Those are useful for scattering problems and calculating radiation from arbitrary currents and things. But here we're assuming that this is a matrix, this is a vector, so you have to multiply them in that order. Okay, so this equation should make sense. Since the pointing vector corresponds to energy flux in the medium, the first term on the right-hand side must be equal to dUE dt, right? We already saw that. This term is epsilon 1 Eij dEj, that is the derivative. It's this expression, right? du dt. E cross H is the rate of change of flux. Okay, so divergence E cross H, right? Just what I was saying. You have a volume, you have E cross H, power flowing, pointing vector, it's leaving the volume, right? If power is flowing out of the volume, the energy density must be decreasing in the volume, right? Because power is the flow of energy, right? With time or whatever, right? So this divergence of E cross H is this term, dUE dt, the rate of change of the electric and magnetic energy densities. So it's this. So, okay, 1/2 epsilon, we replace this with that, and that's equal to this expression. I think you can recast this into this expression, right? By kind of this nature here. If you do that, you'll derive this property. All of this discussion is to just derive this property that this permittivity tensor must be symmetric. The dielectric tensor is symmetric and thus contains only 6 independent unknowns, because symmetric means that A transpose is equal to A, which means that EXY is equal to EYX, and EXZ is equal to EZX, and EYZ is equal to EZY. So there are only 6 independent parameters. For what? What did we assume here to derive this expression? Homogeneous, non-absorbing, and magnetically isotropic. All right. If the medium includes loss, complex epsilon, remember, whenever we include loss, permittivity becomes complex. Epsilon prime minus J epsilon double prime, right? If it includes loss, then this is the relation, Eij equal to Eji conjugate, and that's called a Hermitian tensor. So systems that obey conservation of energy are described by Hermitian tensors. So there is a branch of research called parity time symmetric systems, where you still get similar behavior out of non-Hermitian systems. And if you're interested in these kinds of things, you can dig into that as a follow-on to this, right? There is non-Hermitian electromagnetics, but for us, if it obeys by conservation of energy, then it's a Hermitian tensor. You can still have conservative systems with non-Hermitian tensors, is what I'm saying, but they have to be parity time symmetric, which means there's balance, loss, and gain and things. But that's a fact we'll learn later, all right? Okay, good. All right. Now, so I'm gonna bring in some linear algebra, which is always fun, right? The best 2 courses you guys, I wish I could have talked to you as undergrads. And then when you got here, you would have been appreciative of the statement that the 2 courses that you need to really pay attention to is linear algebra and linear systems. Fourier transforms, Fourier series, all of those things, right? Those, for us, we solved the wave equation in time harmonics, assuming e to the j omega t. That forced our solutions in rectangular coordinates to be e to the j beta x, j beta z. We ended up with exponential eigenfunctions of the wave equation. And we know by solving a differential equation, the weighted superposition of two linearly independent solutions is also a solution. So now I can add up a bunch of exponentials with different amplitudes, and I can create any electromagnetic field I want. So at first, when we solved the wave equation, we only end up with e to plus e to the jkx, e to minus jkx. Like, how can every electromagnetic field be that? But because a weighted superposition of those is also a solution. But what is a weighted superposition of exponentials? That's a Fourier series. So now all of Fourier theory becomes directly applicable to electromagnetic theory. So the better you are at Fourier transforms and Fourier series and things, understanding those, the more power you'll have in solving electromagnetics problems. Remember, we went over that. We looked at the plane wave spectrum, how to expand electromagnetic fields in terms of these exponential bases. And we made the analogy with Fourier transform. It ended up recasting the radiation integral or the expansion integrals into Fourier transform. Linear systems also is a super useful, or sorry, linear algebra is a super useful course, especially when you start solving these things on computers. Then the better you are at that, the more insight you'll have into what you're doing. Everything becomes a linear system on a computer. All these differential equations, partial differential equations, you always recast them into some kind of big old linear system that you have to invert. And the more clever you are at doing that, the better programmer you'll be. There's only so much we could do analytically, right? Eventually, you're going to need to turn to the computer. And there's two ways to approach these problems in engineering. One, you learn how to operate the software, but you don't know what's under the hood. It becomes a black box, and you're just feeding inputs and deriving outputs, and you're trying to draw analogies or correlations between these inputs and outputs, and hopefully support your research hypothesis. All right? That's a bad way to approach the problem. The converse is white box. You know what the program, you know what CST or HFSS is doing because you understand the computational electromagnetics algorithms. But that requires time and effort, right? And furthermore, it's not something you can just read about. You have to practice. You have to implement. You have to write your own codes, really understand it. That is my best advice to you guys. If you really want to become very good in electromagnetic theory, antennas, scattering, is to explore computational electromagnetics. Even if you're not going to specialize in it, you want to know what the software is doing when you solve it. There's limitations. There's things that the software is, you're going to get a solution out of the software and you might not know that the solution is inaccurate because of a certain thing that you assumed was, you get an instruction manual how to run the software, but you don't know what it's doing, right? So we'll be learning all these algorithms, not all of them, next semester. In 5106, we're doing GTD, GO, we're doing method of moments. We're going to do a lot of method of moments. And we're going to learn finite elements and things like that in the numerical electromagnetics course in this department, which I'm going to try to revamp whenever I get a new teaching assignment. So that'll come out. Somebody's going to teach it. I don't think it's been taught for a few years because we need you guys to get excited about electromagnetics and sign up for it. Because if we get 2 or 3 people, they won't let it go. So anyway, to good advice though, all right? Very, very good advice. So let's do this one slide and then we're done. This permittivity is a full matrix here, right? Epsilons are in all 9 positions. We know 6 of them are independent for lossless media that conserve energy. But we know that a matrix like this can be diagonalized. If you remember from your linear algebra, the diagonalizable matrix, the matrix A is diagonalizable if and only if there exists a matrix P such that P inverse AP is diagonal. All right, what does that mean? So let's say then that this matrix can become diagonal. That expression says that P inverse times A times B equals to a diagonal matrix. So let's just say that the diagonal matrix is lambda 1, lambda 2, lambda 3 on the diagonal. All right. Now, I can left multiply by P inverse both sides. If I do that, then I get AP equal to P, or sorry, left multiply by P on both sides. Then I get AP equal to P into this. What is this? This should get you excited. It's an eigenproblem. Very good. some operator matrix A operating on a vector P, we don't know the vector yet, is equal to that same vector scaled by some coefficient, some scalars, right? So now we can write, so let's write P as a block matrix and its column vectors, well, column vectors AI, all right? So this matrix P here could be a matrix. It is a matrix because we result in a matrix, right? This matrix here, we're gonna write in terms of its column vectors. So I equal to 1, 2, 3. For I equal to 1, it's the first column of A. We're calling it alpha I, so forth. And hence, the column vectors of P are eigenvectors. This is an eigenvector problem here, right? Because this is now a vector. So for each column of P, we can create an eigenproblem. A into a vector is equal to lambda into a vector. So those are easy to solve. We solve those a lot, right? What happens when we solve that? What are we getting? What do you get when you solve this problem? A is known, right? When you solve an eigenvalue problem like this, what are you trying to obtain?
Decomposition of orthogonal components.
So a general one, ax equal to lambda x. We find the eigenvalues, lambda, and we find the eigenvectors, x, right? So we're gonna get eigenvectors and eigenvalues here when we solve this, all right? So when we do that, we'll find that the eigenvectors are the new coordinate axes of which in that coordinate system, the permittivity becomes diagonal. All right, so that means P inverse epsilon into P is this. You solve these eigenproblems here, and you get the new principal axes. The 3 eigenvectors, you can arrange them into an XYZ coordinate system, and they are called the principal coordinate system. If you describe your permittivity in that coordinate system, then it must be diagonal, because that's what the definition of this diagonalization is. Therefore, if I rotate from XYZ into X prime, Y prime, Z prime, then my permittivity tensor will become diagonal, and that is where you do all your operations, your mathematics, in that new coordinate system. And we'll see that next semester or next lecture.
Sorry, if we assume the homogeneous loss, non-absorbing.
Okay, I have to think about that. This is all matrix properties on just this matrix here, right?
What if it's symmetric with, sorry.
Yes. Let's think about it. Let me go and then we'll talk about it. So next lecture, don't forget, we have one more lecture. Then the following Monday, a week from today, Tuesday, is your midterm. Show up with your computers so you can have your notes and books. Be ready to solve problems for an hour and 15 minutes, okay? And then we'll continue on. All right, guys, if you have any questions, email me and stuff. Your homeworks are here, pick them up. Yeah, homework 2. And the online students, if you want your homework, email me, I'll scan it and email it to you. All right, thank you guys.
So when we do the decomposition, we're assuming a linear system and.
Thank you. Yeah, thank you for showing up. Yeah, we'll talk. I'm gonna email you back today.
Sure.
Yeah, yeah.
Take your time.
Yeah, it'd be great. Thanks for coming.
The properties of a diagonal matrix when we do it, that's only when we have assumed the things where we have it flipped.
What do you mean flipped?
The symmetric matrix.
I don't know if that diagonalization requires the matrix A to be symmetric. I have to think about that.
Okay.
It's a good thing to explore.
I remember there was something about Hermitian matrix and principal components, but
Yeah, maybe Hermitian matrices diagonalization process is different. That's a good point. Let's think about that. I'll look it up and I'll bring it next lecture. We'll make that clarification. Very good.
Hi, Professor. Are you still having office hours at 11:30 today?
Office hours to no, they're only on yeah, they are. Today is Tuesday, rather. Yes, we will
Okay,
be having office hours.
All right, thank you.
All right.
Is there any practice problems you recommend? Yeah.
Just read through the notes. Be familiar with the notes. So those problems that I assigned, they're not like technical book problems that you can find in other books. They're like derivations and understanding these equations that we're working with, right? So it's probably hard to find another practice set or point you in that direction.
Okay.
So I think study the notes and just know where to find things quickly that are in the problems, and that will help you the most. All right.
So, will that be the job?
Should be in my office today, yeah. Yeah, sounds good. All right. You too. See you guys. Yeah.